Welcome to the wonderful world of analysis. In this video we're going to look at the Cauchy condensation test. Now the idea of what we need to do here is we started looking at series. We've built up a lot of tools and a lot of intuition on what's going on with sequences. We now need to start talking about series. And at this point we have just a few things that we can work with. We have the nth term test, which tells us when a sequence diverges. We have the comparison test, which gives us something where if we have a known series that converges or diverges, it'll help us determine if another series converges or diverges. Now to use this really effectively, we need to have a large class of sort of known sequences and known series that we understand whether they converge or diverge. And at this point, we really only have the geometric series, so we're trying to build up our base to get a little bit more. So our Cauchy condensation test, the hypotheses are there. Basically what it's telling us is instead of looking at the series itself, we can look at a few terms of it and determine whether or not our sequence converges or diverges. Now the following picture, stolen as you'll see from Wikipedia, is actually pretty helpful here to see this. So over on the left we have our sequences A1, A2, A3, and so on. We're adding these up, they're positive and monotonically decreasing, and this is saying, well, we'll take the first one, then we'll take the second one twice. We'll take the next one 4 times. We'll take the next one after that 8 times. We're going to start adding these up. Okay, and the idea is, if we look at this much smaller sort of subsequence, we can determine whether or not our original series converges. Okay, so let's see how this proof works. Okay. Now the strategy, before we actually get into the proof, what we're going to do is we're going to show that some sequences of partial sums, and at the end of the day, that's the only thing we can work with. We look at limits of sequences of partial sums for each series are roughly the same size. Okay, so that is, we're going to look at some sequences of partial sums, S sub n and T sub k, which are defined here, and we're going to show that we can bound one above and below by the other. So they're roughly the same size. So let's start proving this. We're going to start with S sub n, which is going to be the sum L equals 1 to n A sub L. So we've got A1 plus A2 up to AN. T sub k is going to be the sum L equals 0 to k, 2 to the L times A sub 2 to the L. So this is just, A1, 2 times A2 plus 4 times A4 plus dot 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 up to 2 to the k times A sub 2 to the k. Now, there are 2 different cases we need to consider here. So it depends on how these 2 numbers n and k compare to each other. So we're going to do case 1. Case 1 says if n is less than 2 to the k. Okay? If n is less than 2 to the k, let's look at our sequence S sub n. Okay? S sub n is less than or equal to, well, let's see, let's just group these a little bit differently. I've got A1 plus A sub 2. I can pair that up with A sub 3. Okay? And then I would pair up A sub 4 with A sub 5, A sub 6, A sub 7. Okay, and I can keep pairing these up. Plus, let's see, at the end of the day, I can get all the way up to A sub 2 to the k plus A sub 2 to the k plus 1 plus dot 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 up to A sub 2 to the k plus 1 minus 1. And that minus 1, that's not in the exponent. Okay. Now the idea is what I'm doing here is I know my sequence is monotonically decreasing, so this is less than or equal to A1 plus 2 times A2. Plus then I would have 4 terms with A4, A4, A5, A6, and A7. All those are less than or equal to A4, and I can just keep going. Plus dot dot dot. This last one we're going to have, let's see, they're going to be 2 to the k terms in this, so we'll have 2 to the k times A sub 2 to the k. And now the idea is this is exactly that sequence T sub k. So what we've shown here is this tells us that S sub n is less than or equal to T sub k. Okay, so that's helpful. Now on the other hand, if we look at case 2, let's say n is greater than 2 to the k. Okay, then let's look at our sequences, see what we can do. Okay, if n is greater than 2 to the k, let's look at my S sub n. Okay, my S sub n is going to be, see, it's got to be greater than or equal to, I'll have A1 plus A2 plus, let's see, A3 plus A4 plus, let's just keep going, plus dot dot dot, A sub 2 to the k minus 1 plus 1 plus dot 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 up to a sub 2 to the k. Okay, so I'm grouping them again suggestively so I can pair them up. But what's going on here is, since n is greater than 2 to the k, I'm just taking off some of the terms of s sub n, so this has to be greater than or equal to, because my sequence of terms, they're monotonically decreasing and they're positive. So if I drop some off at the end, this has got to be bigger than or at worst equal to. Okay, but now what I know is I can start dropping things off and make these smaller. This is less than or equal to a1 is certainly smaller than 1/2 a1. And I can have a2 here, leave that one alone. a3 and a4, these guys are less than 2a4, okay, because a3's got to be greater than or equal to a4, and I can keep doing this. The way I've paired these guys up, let's see, in this pairing here I have 2 to the k minus 1 terms, so I've got 2 to the k minus 1, and the smallest term in here is a sub 2 to the k minus 1. Okay. Well, this is exactly 1/2 t sub k. So in particular, this tells us 2 times s sub n is greater than or equal to t sub k. So we're in pretty good shape here because we have the following result to rely on. By theorem 324 in our book, a series of non-negative terms converges if and only if its partial sums form a bounded sequence. So if t sub k converges, okay, then this forms a bounded sequence, and since s sub n is bounded above by this sequence t sub k, s sub n has to be a bounded sequence, so our original series has to converge. And if we're assuming that our original series converges, then this 2 times s sub n forms a bounded sequence as well, because 2 times a bounded sequence is a bounded sequence, so t sub k forms a bounded sequence. We get for free that the condensate series has to converge as well. So that's what we needed here, that's what we wanted. Now the reason this is good is this gives us some very important things like the p-test. The p-test says the series of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. Now in calculus you might have proven this or seen this argued by using the integral test. Now of course we haven't proved a thing about integrals, so we can't use that. But the beauty is this Cauchy condensate test is exactly what we need. Okay, so what we do is we look at, instead of this series 1 over n to the p, we're going to look at the Cauchy condensate series. Let's say sum k equals 0 to infinity, 2 to the k, 1 over 2 times k to the p. Now the reason this is going to work out very nicely, we have some nice algebraic properties we can use here. We can combine these powers of 2. This is sum k equals 0 to infinity. Let's see, I'll have 2 to the k minus k times p. So this is the sum k equals 0 to infinity. Let's see, we'll have 2 to the 1 minus p times k. Now the beauty is this is a geometric series. And what we know about geometric series is they're going to converge if and only if the thing we're taking to a power is less than 1. So the thing we're taking to a power is this 2 to the 1 over p. So 2 to the 1 minus p is less than 1 only when, in fact, if and only if, 1 minus p is a negative number. That's the only way we can make this happen. Okay, because if 1 minus p is 0, 2 to the 0 is 1, and if we have a positive number, 2 to a positive number is greater than 1. So now we have established pretty nicely from the geometric series, we have the p-test. Now once we have the p-test, we can extend this. A nice extension we can do is we can start talking about logarithms. So we'll define log n to be the logarithm of n with base e, e being the natural number. So that is, if f of n is e to the n, then log n is f inverse of n. Okay, you can prove that e to the n is a one-to-one function. The logarithm is well defined as well. Now from this, we can go ahead and define that the series 1 over n times log n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. Now again, you might have seen this in a calculus class. This you can do very nicely with the integral test and doing a little u substitution, but we're going to prove this from the Cauchy condensation test. So again, we're going to look at the Cauchy condensate series. Sum k equals 1 to infinity, 2 to the k, times 1 over, well, let's see, we'll have 2 to the k times log 2 to the k, all raised to the p. Okay. Now what we need to do is a little bit of rearranging. Let's see, these 2 to the k's we can cancel out. This is going to be exactly the sum. K equals 1 to infinity, 1 over. Let's see, we'll have log 2 to the k, so we can use some properties of logarithms, make that k log 2 raised to the p. Well, now we can distribute this out. 1 over log 2 to the p comes out in front. That's just some number times the sum. Let's see, k equals 1 to infinity, 1 over k to the p. And then this follows simply from our Pete series test that we just proved.